all bacteria have flagella. Many do, but not all. The number and origin can vary. Give me a second. So we can have monotrichous, amphitrichous. That's one on each side. Lophotrichous is two or more. Either on one side or on both sides. See, spirochetes would be lophotrichous. And finally, paratrichous. For those of you who remember A&P, the prefix peri means on top of or surrounding. In this case, surrounding. See, that was the paratrichous. So that's why number and origin can vary. Spirochetes, I just mentioned lophotrichous on both ends, but they go to the middle. That's the one that overlaps and it kind of scrunch down and uncoil. So the flagella itself has three parts. The filament is the tail. That's what you see kind of swimming around. It's the tail. Question? The hook connects to the filament and it also connects to the basal body. Those are the three parts. Let's just take a look at the picture of it. So there's the filament there. So again, the tail part of it. Skip that for a second. This is the basal body. So it goes through the cell wall and even through the cell membrane. Notice here it's being labeled as the plasma membrane. Same thing. Plasma membrane, cell membrane. I personally prefer cell membrane. A lot of people prefer plasma membrane. Either way. So the basal body is the anchor. It goes all the way through cell wall and cell membrane. The hook connects the basal body and connects to the filament. So to put it differently, the hook is connecting the filament to the basal body. The hook is connecting the filament to the anchor. Again, your basal body is anchored in the entire cell wall and cell membrane. So the filament is very tightly bound by the hook to the basal body. The filament itself is a hollow tube made out of a protein somebody very cleverly called flagellin. Now this part's actually a little bit interesting. You know, last week or whatever it was, we were talking about proteins denaturing, and that usually when you denature a protein, you cannot renature it. And I said usually, but you know, there are exceptions. This is one of the exceptions. Putting the flagella into certain environments, salt and so on, the flagella will actually come apart. It will dissociate. It will come apart. If you put the pieces into a different environment, if you take out the salt or whatever, this will renature. The pieces will come back together again. So this is one of the very few examples of a denatured protein that can renature. Mostly they don't, but this one can.
Flagella want to go inside.
Go inside.
Still, the picture?
Oh, it's an anchor. It's not going inside. See, that's the whole thing is the flagella, but this part is the anchor. If that did not go inside here, the filament would simply come off the cell. It would not be attached. This is how you attach the filament to the cell. I'm not sure I understand the question.
But so like the question I think is what?
Coming right to it then. I just happen to have it right here. Used for locomotion. Imagine a tadpole or pollywog. Those tails are used for swimming. The tails are used for swimming. They have to be attached because as they start swimming, if they're not attached to the cell, they come off. Now, eukaryotic cells, like for example sperm, make a waveform. The flagella goes up and down like this. The prokaryotic, the bacteria, make a propeller motion. They rotate. And they can rotate in either direction. Pardon me?
Oh, I wonder if what do you pronounce it?
Local triggers? They both can rotate, yeah.
Rotate opposite direction?
No, they'll usually rotate in the same direction. Yeah. Yeah. So the bacteria are motile either towards or away from the stimulus. So in other words, an attractant or a repellent. If it's an attractant, the bacteria goes toward the stimulus. If it's a repellent, the bacteria goes away from the stimulus. It's kind of like pizza and spinach. One will be an attractant, one will be a repellent. And these stimuli are called taxes. Now, actually, that word right there, taxes, is singular. Plural, it's the same word. Except then it's pronounced taxes. So how do you know the difference? Well, context. Just depends on what you're talking about. But a stimulus is a taxis. A stimulus is a taxis. Examples of taxis, now it's plural. Examples of taxis. Phototaxis. So now light is your stimulus. Aerotaxis. Well, obviously air, oxygen. Thermotaxis, well, heat, therm. pH taxis, I'll let you figure that one out for yourself. Magnetotaxis, again, obvious. So the point is, lots of different stimuli, lots of them. These are all different taxis. The one we're going to talk about is chemotaxis. So clearly chemicals, and every organism has chemicals all over the place. And enzymes. Enzymes are chemical molecules. So attractant and repellent, but that could be true for any of these. Any stimulus that attracts a bacteria would be an attractant, and any bacteria that repels the bacteria would be a repellent. We're going to look at chemotaxis. And a bacteria can have several taxes at once, can have several stimuli at once. For example, the bacteria might see some food off somewhere in hot water in acid. So the food would be an attractant, but the hot water and the acid would be a repellent. So basically, the bacteria have to prioritize, have to decide what's more important, the food or getting burned alive in the hot water. You know, we do the same thing. You know, a lot of times we'll be cooking, well, we don't get burned alive, but, you know, we'll be in the kitchen and the phone rings, the doorbell rings, and the dog starts barking. And you gotta kind of decide, what are you gonna take care of first? So we also prioritize when several things are going off at once. Well, the amazing thing is the bacteria also prioritize. Okay, it's going to start getting tricky now. It's going to get really tricky. So, and what's even worse is this stuff is not in the book. So, you're supposed to ask questions anyhow, but ask more than usual here. Because it very well could happen you're going to get lost. So let me know when that happens. So, when the bacteria moves, it's going to move smoothly for a second or two. And that's called swimming or running. I'll just say swimming, but either one. And then it starts thrashing around. It starts thrashing around in all directions. It's called tumbling. So every second or two it swims and then it tumbles. The cell then is facing some new direction and it moves off again for another second or two.
Swimming.
What? Swimming. Swimming. And then it tumbles. That's the life of a bacteria. Swim and tumble. Swim and tumble. But right away, what's unusual here, the tumbling occurs at equal intervals of time. Somehow, a one-celled organism has a timing mechanism. Now, we all do. Most of us will wake up in the morning before the alarm clock goes off. We have a 24-hour clock thing. But we're talking about a one-celled organism here. They don't really have alarm clocks. But yet,
Yeah, but they prioritize, so.
they do prioritize. So they're very smart one-celled organisms. So anyhow, they are able to keep track of the time somehow. And that's how they tumble every couple seconds. Now, as usual with numbers, you can ignore the number, but basically without, excuse me, without the attractant, the bacteria can move about 20 nanometers per second. Not very much. Again, you don't need to remember that. It's just information.
But if it has been attracted?
Glad you asked. Don't go away. When the attractant is added, the bacteria can swim longer before tumbling. So the frequency of tumbling decreases. Normally, no attractant. Let's say normally will swim 2 seconds before it tumbles. Now with an attractant, it swims 4 seconds before tumbling. So here is tumbling every 2 seconds, here is tumbling every 4 seconds. So the frequency of tumbling has decreased.
Is tumbling bad for the bacteria?
No. No, it's just that it happens. It happens. It's actually a good question. Is it bad for the bacteria? No, as it turns out, that's how bacteria change direction, by doing the tumbling. They can't turn like we do. They have to tumble. No, they just thrash all over the place and just spin all over, and then when they stop spinning, they're facing in some different direction than they were before.
So it's going to not take as long to get to the attractant.
Yeah, they'll swim longer before they tumble again. Yes.
What if they tumble and then they start going backward?
You're on hold. I'm going to come to that very question in a little bit. So you're on hold for right now. I'm going to come to that. If we add repellent, guys, thank you. Now the frequency of tumbling increases
With the repellent.
with the repellent. So now, for example, it's going to tumble every second. So with the attractant, it tumbles less. With the repellent, it tumbles more. I know you're all wondering, where am I going with all of this? Besides, who cares, but that's a different issue. I do have a goal in mind, so kind of bear with me. Now, after a period of time, it doesn't go on forever. After a period of time, the normal frequency of tumbling will be restored, even if the stimulus is still there. It's called adaptation. So what you're going to get with any stimulus is an immediate reaction, either positive or negative, some reaction, then after a while it stops reacting. It adapts. It's basically like having a car alarm go off. When was the last time anybody responded to a car alarm? Nobody does. Because we all know it doesn't mean anything. Well, we've adapted. That's adaptation. We do the same thing. Or driving through Tacoma smelling that paper mill. Well, we ignore it. We tried to. But that again is adaptation. So basically, adaptation is having a stimulus and you ignore the stimulus. There will be some response, at least for a little while, and then adaptation, the bacteria stops responding. So what that means is the original response to the bacteria is transient, is temporary. It responds for a while, and then it stops responding. Now, what's odd about this is the period of adaptation is longer for the attractant than for the repellent. Now, that phrase, period of adaptation, that is the period of time that the bacteria is still responding to the stimulus. The period of adaptation is the period of time while the bacteria is still responding. Once adaptation occurs, then it stops responding. So basically, during this period of adaptation, the bacteria has not yet adapted. So the period of adaptation is the period of time while the bacteria is still responding to the stimulus. So what this really says is the bacteria will respond longer to an attractant than to a repellent. And that's exactly what it says. Frankly, I've never understood that, just conceptually. You know, a repellent might be something dangerous. That's why it's a repellent. And it seems to me it would make more sense to respond longer to something that's dangerous than to something that might be good. I mean, we prefer something good. But if it's dangerous, we need to get out of there. So the bacteria doesn't do that. It responds longer. It adapts quicker to the repellent.